Okay, so now, as we mentioned, radiations that sorry, radiations that incident upon an object may be reflected, transmitted, or absorbed. So let's say you have a system in an enclosure. Okay, first this surface will emit a certain radiation flux. Okay, that will call incident radiation on our surface of interest. Now, what will happen? A part of this irradiation will be reflected directly by the surface. Okay, and another part will be absorbed by the surface, while a third part can be transmitted from the surface to the material. Okay, in general, as we mentioned together from a while, the majority of surfaces we deal with are opaque surfaces. When we talk about opaque surfaces, this means that the transmittivity is zero. Okay, so what will happen is that the total fraction will be divided into alpha and rho. So we can say that alpha, so in general, the general equation is alpha plus rho plus tau is equal to 1, because the total percentage is divided into three parts. One is reflected, one is absorbed, one is transmitted. Now, in case they tell you you have opaque surface, then you can cancel out the transmittivity term. This will be 0, and you will be left with just alpha plus rho equals to 1. Okay, so alpha represents the reflectivity, tau the transmittivity, alpha the absorptivity, and epsilon the emissivity. What is epsilon? Your object, after absorbing energy, it can restore a certain part. Okay, so it will emit a certain part, and this is the value, if you want, of the emissivity, which is characteristic of the body and is a fraction of the black body emission, will help you to find what is the radiation flux that is emitted from your surface. So in overall, if we want to calculate the net radiation flux, we have to account first for the absorbed part. So you will absorb alpha times g, okay? And you will emit epsilon times sigma times t to the power 4. This is in watt per meter square. And in watt, it's you multiply by the area. Okay, so we'll see together. If you want to account for the net radiation flux, you should do the difference between the absorbed one and the emitted one. Okay, now E and the interaction of G with each participating object will determine the net radiative heat transfer between objects. And let us express it together. Now, just before getting the expression of the net flux, we'll talk about epsilon and alpha. So epsilon, as we said, is defined as the emissivity, and it's the fraction of the black body emission. It is a measure of how closely a surface can approximate a black body for which epsilon is equal to 1. For cases of non-black bodies, epsilon can vary from 0 to 1. Now, concerning alpha, alpha is defined as the absorptivity coefficient, and it represents the fraction of incident radiation that is absorbed by the surface. Now, when we talk about black body, for black body, we said that the black body is a perfect radiator and also it's a perfect emitter. So for a black body, epsilon is equal to alpha is equal to 1. However, for a gray body, okay, epsilon will be between 0 and 1, and alpha will be between 0 and 1. And in general, both epsilon and alpha will be depending on the temperature. However, to simplify things, in most of the application, we take epsilon equal to alpha. Okay, so whenever they don't give you any information, you can consider that epsilon is equal to alpha. And rho represents the reflectivity fraction. So as we mentioned, you can say that rho plus alpha equals to 1. And in case you have, let's say, for example, in case they give you rho, you can calculate alpha and you can deduce the emissivity. Okay. Now, for case of transmissivity, as we mentioned, for opaque surface, the transmittivity is equal to 1. Now, if we want to compute the net radiation flux, okay, as we discussed, we have that a part will be absorbed by radiation, okay? To calculate the flux absorbed by radiation, we should multiply G. G, if you want, unit is watt per meter square. It's the flux that is reaching your surface. But as we mentioned, a fraction of it will be reflected and another fraction will be absorbed. The absorbed one is equal to alpha times G. So alpha times G will give you the absorbed value in watt per meter square. Now, if you want to get the absorbed rate in watt, all you have to do is to multiply by the area. So in total, the flux that will enter the surface due to radiation is alpha times G times A. Okay? Now, in general, this flux is coming, if we take the example of large enclosure, okay, G is coming from the surrounding, which is radiating, which is emitting heat, okay, due to heat by radiation, due to their temperature T surrounding. So how we can write then G, okay, we can write G as equal, okay, to sigma times T surrounding to the power 4, okay? And because we have our area will absorb just a fraction, okay? Then we multiply by alpha. When we multiplied G by alpha A, we will get Q absorbed, okay? So G that is coming from the outer environment is emitted by radiation. And we can compute it, if you consider, let's say, the large enclosure, we can compute it as a sigma times T surrounding to the power 4. While the radiation that is emitted by the surface, okay, will be equal to epsilon times A times sigma times T surface to the power 4. And as we discussed together, we'll consider that epsilon and alpha are equal. So you will have in common sigma alpha, which is treated equal to epsilon, and the area. Okay, so the net radiation can be computed as follows. You can say that the net radiation is the difference between the two, because you have Q that is emitted and you have one that is going out from your surface, while another that is absorbed by your surface. So in total, the net radiation flux will be epsilon sigma A times T surface to the power 4 minus T surrounding to the power 4. Now, for many applications, it will be convenient to express the net radiation as a heat exchange in the following form. Q radiation equal to a certain coefficient HR times AS times TS minus T infinity. Look, we already know that convection is H convection, okay, times A times delta T. And therefore, we can see a linear relation between the convective flux and the temperature. It's true that radiation flux is not linear because it's proportional to T to the power 4, okay? But sometimes in modeling, dealing with a fourth order term is really complex. So let's say you are writing a model and you want to solve for heat processes. if you can linearize the radiation term, this will help a lot into numerical calculation. Okay, that's why to linearize the radiation heat flux without if you want compromising the accuracy of its expression, what you can do, you can just play a little bit with the formula. And we have seen together that we can write the rate as epsilon times sigma times area times T surrounding to the power 4 times, sorry, T surface to the power 4 minus T surrounding to the power 4. Okay? So instead of dealing with fourth order term, you can just say, let me decompose this, okay, and try to linearize it. So you can say that I can write this is a4 minus b to the power 4. So I can write it mathematically. This is equal to, if I expand it in this way, T surface square minus T surrounding square times T surface square plus T surrounding square. Okay? And now you can expand more and say, let me expand here. This is in the form of a square minus b square. If I expand it, I get T surrounding minus T surface minus T surrounding times T surface plus T surrounding. Okay, so what will happen then, that if you take the whole term other than Ts minus T surrounding, you will have Ts minus T surrounding multiplied by what? It will be multiplied by Ts plus T surrounding, okay, times what? Times this term, which is Ts square plus T surrounding square. So you will get, as if you want, HR can be considered as epsilon times sigma times T surrounding plus T surface times T surface square plus T surrounding square. Okay, and in this way you can have the temperature effect and the nonlinear effect will be computed just in the coefficient HR, while you write your radiation coefficient in a linear form function of delta T. Okay? Any question on this? So just you did some expansion in order to write a Q in the form of HA delta T only, but H will be function of the temperature of the surface and surrounding, and it will be proportional, if you want, to temperature to the power 3, because you want to have here a linear term. So you transform T to the power 4 as H, which is function of T to the power 3 times delta T. So in summary, this table will summarize the different heat transfer processes that we discussed today. We have several possible of heat transfer processes: conduction, convection, and radiation. We can say that conduction is mainly due to diffusion of energy because of random molecular motion. The rate equation is Q second in watt per meter square equal to minus k dt by dx, and the transport property is the conduction coefficient. For convection, we talk about diffusion of energy because of random molecular motion plus energy transfer due to bulk motion. And the equation of convection is Q second equal to H times T surface minus T infinity. And the main transport property is the convective coefficient H. While for radiation, it's about energy transfer by electromagnetic waves, and we can express the rate of radiation, the rate as HR times A times Ts minus T surroundings. This is the linear form. And the heat flux is equal to epsilon times sigma times T surface to the power 4 minus T surrounding to the power 4. The characteristic properties will be the emissivity and, if you want, the lumped radiation coefficient HR. Okay, so in this way, we have done a small review on the different heat transfer mechanisms. We should know that not all 3 heat transfer modes can exist simultaneously in the same medium. A solid may involve in general heat transfer by conduction and radiation only. However, a solid may involve heat transfer by convection and or radiation when its surface is exposed to a fluid or other surfaces. For example, if you consider the outer surfaces of a cold piece of rock, it will warm up in a warmer environment as a result of heat gained by convection from the air and radiation from the sun. But the inner parts of the rock will mainly warm up by conduction. Okay. Now, at this stage, we are ready to remember the first law of thermodynamics. Whenever we talk about the first law of thermodynamics, it's just equivalent to conservation of energy. Okay? And when we treat a closed system, what we mean by a closed system, you consider a certain mass and you look how this mass is exchanging energy with the external environment. We know that energy can be transferred in 2 main forms, in form of heat and in form of work. We already discussed today the different forms of heat. So you can have possible heat transfer by conduction, by radiation, by convection, and you can also have exchange of energy in work form. Example, how we can have exchange of energy in work form. If you take the example of piston cylinder systems, okay? So you have a piston and you have air inside your cylinder. When you press on your piston, okay, you will transfer energy to air because as you put force on your piston, you will compress air. And when you compress air, you will increase its pressure and temperature. So you will increase its energy. So here you increase the energy of air because of what? Because of a work done by a force. Because you know, whenever I apply a force on a certain area, so I have a pressure and I am inducing displacement. Force with displacement will lead to work, okay? And we'll see together that work can be mainly calculated as integral PDV in a closed system, okay? So whenever you have change in volume due to action of pressure, you can have production of work. So here, any system can exchange, closed system, can exchange with the surrounding energy in form of heat or in form of work. So we'll discuss more in details how to calculate work in a future chapter. But now we should know that because of energy conservation, we can say that the total amount of energy change stored by a system, so the energy that is stored by a system is mainly due to a balance between heat and work. So if you put, let's say, heat on your system, this will lead to increase of its energy. If your system will lose heat, this will reduce its energy. Another way to change energy of your system is to put work on it, or if your system itself can produce work, it will lose energy. Now, why in this equation we are putting minus W? It's just a matter of how to define work, okay? Because some books consider that when a system produces work, when it will give the surrounding energy in form of work, I consider this work as positive. Okay, if you want to follow this convention, you should pay attention to put a minus before W in your equation. Why? Because in general, to increase energy of your system, you should give it, you should put work on it. Or you should give it heat, or you should put work on it. But if you take the convention that work is positive, when it's produced by your system. This means that when you put work on your system, you will consider it as negative. But since this work will increase the energy of your system, in order to lead to an increase in this equation, you should put it as minus W. On the other hand, if you use the other convention, in other books will say that everything coming in the system increase its energy. So I will put Q plus W, and then I consider that any work done on the system is positive and any work done by the system is negative. Okay, so to summarize, whatever is your convention, you'll get the same result at the end. Why? Because everything entering your system will add to its energy. So at the end, it will be added as a positive quantity. Why? Because look, if you take the convention of the book here, that the work done by a system is positive. If your system produces an energy of 10, okay, then you will consider that your system, for your system, W is equal to plus 10, okay? But when you go to the energy balance, you will say that delta E is Q minus W. So when you apply here, you will do minus 10. So at the end, it will be accounted as a flux leaving the system. So it's minus 10. Okay. If you use the convention, the second convention, Q plus W equal delta E. In this convention, W is counted positive when it enters the system. And since here the flux is leaving the system, okay, W will be accounted in this convention as negative. So you will put plus minus 10. So at the end, both will give you minus 10. The only difference is which W is considered positive and which W is considered negative. When you consider that when your system produces work, W is positive, you should put minus in the equation. And when you consider that W is positive when you put work on the system, then you put a positive sign here. And at the end, when you apply, both will give you the same result. Okay? So we can say that delta E represents the change in the total energy stored by the system. Q is the net heat transferred to the system, while W is the net work done by the system. Why here they said W is the net work done by the system? Because they consider here the negative sign. If you put the positive sign here, you just define W as the net work done on the system. This is the difference between the two conventions. Okay, so the first law can be applied for a control volume or to an open system also. But in case you apply the first law on an open system, what is the difference between open system and closed system? In closed system, as we discussed before, you are exploring the same mass. And this mass can only exchange energy with the surrounding through forms of heat and work. However, when we talk about open systems, in open systems, you can have fluxes of masses that can enter the system or exit it. So for example, if you consider a certain duct, you have mass flow rate coming in and other mass flow rate getting out. Whenever you have mass flow rates, then if you want to assess the variation in energy, you should consider the energy transported by your mass fluxes. Why? Because imagine, for example, that you have a mass flow rate coming at a very large temperature, okay? So it will transport with it the energy of the fluid of high temperature. And this will lead to increase of the energy inside, and therefore the flux that might leave at a smaller temperature because one part of the energy will be stored by the material. Okay, so whenever you have a fluxes, you should account when you calculate the variation of energy, should account for the fluxes getting in and fluxes of mass getting out. So you should add the new terms to your energy balance in addition to Q and W. Okay, and we'll discuss how the energy equation will be affected when you have mass flow rates coming in and out. Now, concerning the energy equation, okay? When we talk about variation in energy, we should know what are the main forms of energy. So when you say, I want to compute delta E stored by a system, you should know what are the forms of energy of storing that you can have in a system to assess the variation of energy stored. In general, the energy of a system can be divided mainly into mechanical and internal. What we mean by this? When we talk about mechanical energy, this can involve kinetic energy and potential energy. Okay? To give you simple examples, let's say if you have a ball and you give it a certain velocity, this means that you are giving it energy in the kinetic form. And the kinetic energy is written as half times the mass times velocity squared. Now, what about potential energy? If you have a particle and you move it upward in a vertical direction, higher the altitude of the particle, higher will be the energy stored in it. Why? Because if you release the particle, okay, larger the height, you can reach larger velocities at the ground level. Because when you release it, the potential energy will be transformed into kinetic energy. So as you increase the elevation, you store energy in form of potential. So when you release the particle, it will move downward. This energy can be transformed into kinetic, and larger the height you reach, larger the velocity you will reach when you go back to ground. Okay? Energy can be stored in kinetic form, can be stored in potential form. Also, whenever we deal with, let's say, any system has a certain internal energy. Internal energy is all other forms of energy that can be for a certain system that are different than mechanical. So we can think about thermal energy, which is related to the temperature. We can think about chemical energy. You know that whenever you have combustion or chemical reaction, you can have production of energy because energy is stored in molecules in chemical form. We can talk about nuclear energy. We can talk about electrical energy, etc. So we have several forms of energy that can be under the title of internal energy. So whenever we want to explore variation of energy, we should check if we have variation in kinetic energy, if we have variation in potential energy, or if we have variation in internal energy. So now, if we want to write the energy equation, we know that energy can be transformed, but we cannot create energy. Okay, so everything is already here, but just we can go from one form to the other. So the first law can be written in the following form: delta E stored, okay, is equal to the energy coming in the system minus energy getting out of the system plus energy generated within the system. So already, when we talk about energy in, we already discussed that for a closed system, energy coming in and out can be in form of heat or work. Okay, what will differ for open systems that energy in and out can be also due to mass transfer. So you can have mass fluxes getting in transporting energy and other fluxes getting out taking energy from the system. Now, what about energy generation? EG is the thermal and mechanical energy generation that is proportional to the volume of the system. And for example, let's say you have a system and you have you put a certain resistance, as we give the example before. In the example before, so whenever you have a current going through the resistance, this will lead to generation of energy within the system. So you can account with it for this in the generation term. Another example, if you have a combustion process inside your control volume, this will lead to energy generation, and you can also put it under energy generation term. In general, the energy generation term will be given in watt per meter cube. Okay, so it will be given per unit volume. Now, we can write the energy balance in rate form. What do we mean by rate form? So we divide per unit time. Okay, so if we just derive per unit time all energy terms, instead of getting terms in joule, we will get terms in watt, because we know that joule per second will give us watt. So if we just say dE by dt, which is derivative of energy storage with respect to time, is equal to the flow of energy, rate of energy coming in, minus rate of energy getting out, plus rate of generated energy. Now, in case they tell you you have a steady state problem, whenever you see steady state, this means that you don't have variation with time. So dE by dt will be equal to 0. Okay? And then you end up with E dot in minus E dot out plus E dot generated equal to 0. Now, how to account for the stored term? In general, for ideal gases and incompressible liquid, you can write the rate of energy storage as rho CPV times derivative of temperature with respect to time. So you can link the storage of energy to the variation of temperature with respect to time through the following term, where rho represents the density, Cp is the specific heat, which is a characteristic of the material, and V is the volume. Now, the thermal energy can be divided, as we discussed before, into sensible energy, which is due to mainly changes in temperature, and latent energy due to change in phase. So these are the formulas summarizing the equations, okay, for the case. This is the energy equation, and this is the energy rate equation for a closed system here, and this is for a control volume where we can have fluxes of energy coming in and getting out. Okay, so we'll stop today here. Next time we'll do practice problems on to discuss all of these ideas. Any question before we close? Okay, guys, see you next
Professor
time.
Ahmad, can I talk to you at the end of class?
Yes, sure.
No?
Sure.
5 minutes alone.
Okay.
I have a few questions.
Yeah. Okay, great. Yes. So let me just stop recording.